Hey everybody, this is John Buck back with another array signal processing video. In this video tonight we're going to talk about beam steering, or sometimes what's called electronic steering, the way that we can take an array of sensors and direct it to look for energy in different directions without physically moving it, and that we do this by adding different array weights to the sensors before we combine them, where those weights are basically different delays to shift things so that the signals from the direction we're interested in get constructive interference or become coherent before we average, and the other directions are not. And so we're going to begin tonight by quickly reviewing the beam pattern and the ideas there, and then talk about how we can design different array weights to look in different directions, and show you some examples of how the resulting beam patterns look for that. Okay, so let's switch over to the whiteboard. So again, for tonight, we're going to focus on uniform line arrays, just like we did in the previous class, where we're going to assume we have a sensor array should not be erased. A linear array of sensors along the z-axis. We're going to assume we have an odd number of sensors, n, so we can talk about putting it with this middle sensor at z equals 0 here. So this is our origin of the z-axis here at the middle sensor. And to make the math a little simpler, we're going to number the sensors pretending like they're a sequence in discrete time going from minus n sub c to plus n sub c. And so again, these are each spaced d apart. And so the nth sensor, as we count from minus nc to plus nc, is located, location z sub n is just n times d here. We're going to be looking for plane waves that are propagating with wave number vector k, the k bolt k here shown in the blue, in this direction, forming an angle theta with the positive z-axis. And so when we do that, it turns out if we think this through, that the projection of that wave number onto the z-axis is minus 2 pi over lambda times the cosine of theta. And to sort of a quick sanity check, asymptotic extreme, when theta goes to 0, that would mean the blue line is coming right down the axis here, so all of the wave number would be in the negative direction. So that's why we have this minus sign here for the incoming plane wave from direction theta, essentially. We can also sometimes, for convenience, write this, we'll call this k sub 0, where this is just the magnitude of the wave vector times cosine theta. And when we define kz this way, the beam pattern k sub z, the equation will be like this. Minus, the sum is little n goes from minus nc to plus nc of w conjugate of n. We're going to write the weight vector here, the weight vector like it's a sequence, like a discrete time sequence, e to the minus j kz dn. So k sub z is our spatial frequency variable here. And when we write it in this way, we also saw last time, we can also think about this as a dot product of two complex vectors. One vector is all the array weights, and the other one is the array manifold vector. And for tonight, for now, we're going to talk about this in the k sub z version. The textbook defines these in different ways. We use different spatial variables. Sometimes u, sometimes theta, sometimes kz. But again, just reminding ourselves, this is the array manifold. This is the weight vector. And this superscript of h is what we use to refer to conjugate transpose. Right, if I were to write out that manifold vector, just to be clear in terms of kz, if I think about how it's stepping through up here as I go from minus nc to plus nc, that the first element in v would be e to the j k sub z d times nc, right? Because putting in minus nc here, the minus signs would cancel. It would count down to, say, e sub j k sub z d, and then a 1, and then e to the minus j k sub z d, all the way up to e to the minus j k sub z times d times nc. So those would be, that's the manifold vector for the plane wave propagating in the kz direction, propagating in a direction whose projection onto the z-axis is k sub z. So this is our manifold vector here. Okay, so that's our beam pattern, mathematically speaking. what I want you to do now is pause the video for a second and remind yourself or think about what is the beam pattern conceptually speaking. Okay, well hopefully you're back now. And again, the beam pattern is the gain, that is the magnitude and phase, applied to a plane wave propagating with kz by the array weights w. So for a given set of array weights w, it looks at all the different directions a plane wave could come from and says what would be the gain applied to a plane wave with this spatial wave number kz. Okay, so it's a function of the direction of propagation in terms of kz, the wave number variable. Another good place I want you to pause the video and remind yourself, well, what is the DSP time domain analogy of a beam pattern? Think about what thing in the DSP world plays the same role that the beam pattern does here in array signal processing. All right, so again, now in terms of developing our sense of analogy, the beam pattern for array processing is like the frequency response for a DSP or for time domain processing, and that both of them are looking at, we have a single filter, whether that filter is W or it's H of N, the impulse response, but either one is telling us this is how the filter will apply or process every possible input. In the beam pattern case, it's all the possible plane waves. In the DSP case, it's all the possible complex exponentials. Okay? And so that we saw also last class, the simplest set of array weights is the one that just averages the sensors without any frequency shifts or phase shifts. And when we did that, if we went through and solved the beam pattern, we'd go through the same finite geometric sum and end up with the discrete time sinc or periodic sinc function. In terms of, if we solve that in terms of kz, we'd get a slightly different expression here, but it'd be sine of n number of array elements, kzd over 2, times n sine kzd over 2 also. And if I look at that, I can get the beam pattern. Let me bring it here. I made an example. Here's an example I made how to show you. So this is for a 21 element array with a wavelength of 0.1. The spacing will be lambda over 2, so right what the spatial Nyquist theorem says. And looking at broadside. So again, my steering angle is broadside, which is the set of array weights we just saw. Right? When we just combine everything without any phase shifts, we're steering the array at broadside, so signals coming in perpendicular to the array are constructively reinforced. And we see that here. The kz is 0, is the wave number we'd see, and this is what we call the main response axis, this peak here. And then going outside the main response axis, like this distance here would be what we call the bandwidth, the null-to-null bandwidth between these first two zeros. We have other nulls and side lobes out here, which is saying plane waves coming from these directions would be attenuated, and we can say exactly how much if we wanted to read off the value of this graph. Another piece of important terminology is this idea of the visible region. We say the visible region is the values of kz where the signal can be propagating, right? If we have 2 pi over lambda times cos theta, that cosine can go from -1 to +1. So that says if I have a propagating wave, it's between -2 pi over lambda and +2 pi over lambda. And that's what these red dashed lines show. The region between the two red dashed lines is what we call the visible region. These are the wave numbers that are propagating. The other important piece of terminology is the grating lobes. And the grating lobes appear at multiples of 2 pi over d, which in this case, if lambda is 1/10, then d is 1/20th. So 2 pi over d is 40 pi, which on this normalized axis shows up at 40. These peaks out here are called grating lobes. As long as we satisfy the Nyquist sampling theorem, that is that we have d less than or equal to lambda over 2, the grating lobes will always remain outside the visible region no matter how we steer the array. Right, so that's another important idea. As long as there's no aliasing, the grating lobes will remain outside the visible region, which means we don't have any confusion about which direction the energy is coming from, that we have strong response in just one direction within the visible region. Okay, so those are important ideas, sort of reviewing from beam patterns from last time, plus a few new words, new definitions, the visible region and the grating lobes. Now let's go on and talk about steering. It's great to be able to get this nice response at broadside, but not all the energy that we're ever going to be interested in is going to come from the direction perpendicular to the array. We need to be able to look in all the directions in the physical world to figure out where energy is coming from. So how can we do that? Well, this shows one way to do it that some of you may have seen if you've been around ships, and there's similar versions often at airports or other places, which is an radar antenna that's just rotating. This is also an array of radar antennas. And one way to do it is just physically spin the array to look in every direction. So the electronics are hardwired to always go to broadside, but then you spin the thing physically to look in all directions and accumulate information from all directions. And historically, this is the old version. You've probably all seen old war movies from World War II where radars did this as well, either physically or spun by motors, or sometimes even really old ones, even by hand in some ways. But there are times where that's not convenient. If our array is mounted on the side of a ship or mounted at the bottom of the ocean for an acoustic array, we may not be able to spin it. We'd like to find ways to look in different directions without moving the sensors. And that kind of electronic steering is what we're going to be talking about tonight. The key to doing that is something we've already talked about a little bit when we talked last week about, we first talked about plane waves that are coming across uniform line arrays, right? If I have my wavefront coming in like this from a direction that is not broadside, I'll see some small delay as the pulse goes from sensor to sensor to sensor. And we said one way we could, if we wanted to look in that direction, to try to look for energy coming from that direction, we could take our measured signals and introduce time shifts to undo those delays for that given direction, what we'll call the look direction or the steering direction, so that any energy coming from that direction would be lined up. The pulses coming from that direction, if they really are there, would be lined up, and so when we average across the array after those shifts, we'll get constructive interference or coherent combination. And so that's the basic idea in electronic steering, is we're going to apply shifts in the time domain or phase shifts in the frequency domain for a given direction so that energy coming from that direction will be coherently combined. So let's see how that's sort of the conceptual idea. Now let's break it down and see how that works a little more mathematically. So the problem for beam steering is that we want to say, well, looking at the case we just saw where we're adding everything in phase to give us our discrete time sinc function, how can we choose a new set of weight vectors so that the new beam pattern is like the old beam pattern but shifted by some amount kt, where kt is the wave number for the look direction, is minus 2 pi over lambda times the cosine of theta t, where theta t is what we call the look direction or the steering direction. Different communities use different, so this is look, not lock, or steering direction. Slightly different vocabulary, but they mean the same thing. So we now want to change the sensors before we combine them so that energy coming from the theta t direction gets constructively reinforced. So let's first think a little more conceptually using our DSP intuition, and then we'll do the hard math. We say, well, if I think of it this way, kz is a kind of spatial frequency. So if I want to shift things in frequency, pause the video for a minute and think to yourself and answer this question. If I want to shift things in frequency, what do I do in time? And we'll see the same thing applies here. We're going to use shifting in spatial frequency. We'll have the same, conceptually, same type of thing in space. All right, now you're back. Hopefully what you remembered is that from your undergrad signals class or DSP class, if I shift in frequency, I'm multiplying by a complex exponential in time or space, depending on which version we'll see. Tonight we're doing the space version, so it's telling us we're going to multiply the array weights, W, by complex exponential, because that's the function that we're sampling in space. Okay, so let's see how that works, because we can sort of do this by combining two definitions. We can say, I want to have, like I wrote above, B2 of kz equal to the original broadside sinc shifted by kt. We also know from the definition, right, that this is equal to the sum as n goes from minus nc to plus nc of W2 conjugate n e to the minus j kzdn. Right, so that's our beam pattern just from the definition in terms of W2. Right, and we also want this to be equal to the original beam pattern shifted by kt. right? And again, these sums are going from minus NC to plus NC. So let's see how that works out. So let's start by writing out the equation for the first thing. We say, well, B1, if we're gonna sort of bring this down here. B1, if we write out B1 of Kz minus T from the same definition, we'd say, well, this would be minus NC to plus NC of W1, right? Because we're now looking at B1, e to the minus j. We're going to replace Kz by Kz minus Kt dn. And so we're going to regroup terms here to get something here in terms that if we write this, we can set it equal to W2. And so using the property of the exponential, we can say, well, this is W1 conjugate of n. And then we're going to pull out the Kt term. So we get an e to the plus j Kz, K sub z. No, we wouldn't. We get the K sub t. The plus sign, 2 minuses cancel, leave a plus, dn. We're going to take this whole thing together, and then we'd still have the usual Kz dn exponent up here. And so basically we can set these two equal. We can say this W2 star has to be this term here, right? This is my W2 star of n. So doing that, we'd see W2 star of n would be equal to W1 star of n, e to the j, the steering wave number, K sub t, times dn. And so taking a conjugate of each side, it says the new weight vector is the original weight vector times e. If I take the conjugate of e to the plus j, I get e to the minus j, K sub t dn. Right? So as we predicted from our intuition, we're going to take the original weight vector and multiply it by a complex exponential, albeit with a different sign than we would have expected, a different sign exponent than we would have expected from the time domain. And remembering that W1 is just all ones except for 1 over n, we could say, well, this would, once I plug that in for W1, I get 1 over n, e to the minus j, kt dn, which we can recognize this is 1 over n times the array manifold vector for the steering direction. So this is an important idea that our weight vector for what this is called the conventional beamformer or the delay in sum beamformer. We'll often abbreviate it just CBF, or sometimes you'll see this called the delay in sum beamformer. SUM sum. But the array weights here are just basically a complex exponential scaled by 1 over n for the manifold vector or replica vector, whichever you prefer, evaluated in the wave number steering direction, or if you prefer later we'll see working with u or theta, the same idea. We just evaluate the manifold vector in the direction we want to do the steering in. And this matches, again, as I said, our intuition that to shift in frequency, we multiply by a complex exponential in the time or space domain, and that's what we've done here. So let's see how this looks if I take my same example. So here is my original broadside beam pattern we saw at 0. If I steer it for, this is for 60 degrees, we'll see that well, cosine of 60 is a half. And so we have minus 2 pi over lambda times cos 60. We end up here at minus 10. If we work that out, minus 10 pi rather. I forgot the pi scaling. So this is we've got the same basic shape, and in fact we see one of the nice things about working in KZ is the main lobe, the null-to-null beamwidth stays the same. Our main response axis is now here, and all the side lobes have the same width going out. They're equally spaced, or the nulls are equally spaced in KZ. We see our grating lobe here has moved also left by 10, but it's still outside the visible region. Because we satisfied the spatial Nyquist theorem, we don't have any aliasing. And just to finish up, let me show you how this looks if we look at all 3 different spatial variables we'll commonly be using. So again, for the steered case here, this is the one I just showed you, steered at minus 10 pi. if I relabel this axis in terms of theta, right, if I just start with theta going from 0 to 180, we can see here's the main response axis at 60. But we see a couple of features here that while theta is very physical and it's nice to think about things physically, one of the problems with theta is that the side lobe widths, or the null-to-null widths, change as a function of theta. In fact, we're not getting into it tonight, but we'll probably see later. We'll look at a homework exercise or something to show the null-to-null beam width for the same array will change with steering angle as I shift my steering, so that I'll have a narrower beam at broadside than I do as I move towards either end fire. And so that's kind of frustrating when I think in theta. I'm not always sure how wide the beam is. Whereas in kz, or if I work in the u direction, which is the directional cosine of theta, I see here, like I mentioned earlier, cos of theta is a half. So here's on this axis going from -1 to 1, this would be theta equals 0 to 180. One of the nice things about u is that, again, we're like seeing kz, we have equally spaced nulls. And so the main lobe width is the same on the u-axis as I shift and as I steer in different directions as well. So that's a lot. I've put a lot in this video. I'm sorry, I probably should have broken it into two if I'd planned ahead a little better. But I'll stop here to say just our main point for this video is reviewing the basics of beam patterns and then going on and showing by adding phases or by setting the array weights to be 1 over n times the array manifold direction, or array manifold vector for a look direction, we can get what's called the conventional beamformer or delay in sum beamformer, and steer the array to look for energy from any direction without physically moving the sensors. We do this all electronically just by how we add time delays or phase shifts to the signals before we combine across the sensors. All right, thanks a lot, and I will see you in class.